and welcome to Engineer Simple. So in the previous video I stopped here where I drew the network sequence impedances and I showed all the impedances for the example that I'm going to go through and kind of apply all the equations or derivations I went through in the previous videos. So I'm just going to continue. So the positive equivalent impedance basically from the previous videos is the positive sequence of impedance A plus the positive sequence of the transformer in parallel with the positive sequence of system B. So again, if you go to the diagram, it will be obvious. So this impedance here plus this in parallel with this impedance. And again, from circuit analysis, this basically is just a product of the two impedances, system A plus Z1 transformer times Z1 of system B divided by the sum. Transformer plus Z1 system B. So if you go back to the diagram, so I'm just going to plug the numbers plus 0.031 times 0.0065, and all these values are in per unit on a 100 MVA base. Then it's just the sum of all these impedances. So if you calculate this, you will get the equivalent impedance, or the positive sequence impedance, is equal to 0.05462 per unit. So here's one, and obviously the negative, this here is equal to negative sequence impedance too. So I'm just going to go ahead and write is equal to the equivalent negative sequence impedance. Now let's calculate the equivalent zero sequence impedance. So again, it's zero sequence of system A plus sequence of H. So this impedance in parallel with the zero sequence of the Y, and you obtain the equivalent, then you just add to it zero sequence of X. And if you want to know how I came up with this equation, I would recommend going back to the previous videos. So this entire thing is in parallel with the zero sequence of system B. So basically zero sequence of system A plus zero sequence of H times zero sequence, so I'm just writing this out, of the Y divided by their sum, system A plus zero sequence of H plus zero sequence of the Y. Just gonna erase this here. So basically this, so that's what you get for that, then plus zeros sequence of x. So basically you will take this entire thing in parallel with zero sequence of system B. So you would take this entire quantity times this divided by the sum of this quantity plus this impedance here. So what you can do, you can just like calculate this here, plug the numbers. Let's just call this M, and I'm just gonna call this N. So once you calculate this here, so then you just have M is in parallel with N, so then it's just M times N divided by M plus N. So basically, if you carry out the calculation, you get a zero sequence equivalent impedance of 0.0139492 per unit. So if you want to redraw the circuit, and for simplicity, since typical reactances are going to be Y higher than resistances, and for calculations, I'm just using reactances. I mean, you can use resistances, it's just the calculations get complicated, but really you will get similar results. So I0, I1, I2 will flow through the circuit. This is just the zero sequence equivalent impedance, which I calculated to be 0.0013492 per unit. In the positive sequence and the negative sequence, I calculated 0.005462 per unit. The negative, the same thing, 0.005462 per unit. So that's the equivalent sequence networks. So from here, so basically these quantities are just, so the voltage divided by, because this current flows through all these equivalent impedances, so it's just the sum of the equivalent positive, equivalent negative, plus equivalent zero sequence impedance. So I said I'm applying 1.05 pre-fault. So basically you just add these here. 0.05462. And if you want, you can, since the positive and negative are the same, you just do times 2 plus the zero sequence impedance 0.0 13492. All those are per unit. And if you calculate that, it will be 43.0045 per unit. So basically this is I0, I1, I2. So you can see how I started from a system, how I drew the sequence networks, and how I calculated the equivalent impedances and currents. So once you go through it, it's simple, but it's the first time you look at it, it's kind of it it appears overwhelming or complicated. So now I have I0. If you go back to the previous equations that I derived in the previous videos, and I'll just repeat here for convenience, the zero sequence current through the low voltage is just a zero sequence of system B divided by the sequence impedance of system B plus zero sequence of system A plus the zero sequence of H, or the high side of the transformer, which is in parallel to the zero sequence of the Y, plus the zero sequence of the low voltage. The entire thing times I0. So you can rewrite this as zero sequence of system B divided by the zero sequence of system B plus, so these are in parallel, so it's just a product. So the zero sequence of system A plus the zero sequence of H times the zero sequence of Y divided by their sum, basically. Plus zero sequence of X, entire thing times I0. So if you plug in all the numbers, this is just 0.0195 per unit. 5 plus 96 plus 0.003 times 0.185 divided by the sum, basically. Zero point zero 32, this is point, basically, times 43.045. And one thing I forgot to mention, this 0.003, what it means, I know in other countries like Europe, Africa, Asia, other countries of the world, they would write 0,003, but in the United States instead of comma, we write point. So just want to clarify that. So if you calculate this, you get I0x equal to 13.25 per unit. So I'll stop here and pick up the rest in the next video. So in the next video, I'll calculate the current through the zero sequence current through the tertiary, then the positive, negative, and zero sequence through the high voltage windings. Thank you for watching.